Okay, so welcome to today's lecture. What the plan is for today is that we will continue first with what we started last week on the state space models. We'll finish this today, and then in the second part, we will take a bit of an overlook. Now we looked into quite different types of sequence models. We looked at CNNs, at RNNs, at self-attention, and now at state space models. So we want to get a bit an overview of how they all are connected, how they are used, and how they're embedded into larger models. And this will then be the end of the part of this lecture on architectures. With this, then you'll have an exercise on Thursday, and then we will look into training after the break of next week. So let's start with where we were last time, and that was here on linear time variant systems, LTV. We started with the linear time invariant systems, and then we saw that there is some challenge with this, and that is that they are not able to, on the one hand, skip some inputs or reset the input. While these LTI systems were very good at some tasks where you need a very long context, some pathfinding and so on, were really struggling with some text processing tasks, for example. And when looking at this, some found out that there is a challenge with reset and filter. And so the next step we can look into is the linear time variant systems. And here you see the main difference. So you see the formula is very similar. We have again a hidden state HK. And based on that, we then calculate our output YK. The main difference is now here in purple that our calculation is no longer constant over time. So now our weight matrices A, B, and C are depending on the current time step. So AK is not, A is not always the same, B is not always the same in C. And this allows us then to, in some way, do this process of resetting the input or ignoring some inputs like filter. So for example, if we want to reset the hidden state, what we will do is that we can say the AK, so the matrix at the current time step, to 0. If this is happening, then our hidden state, we see it very nicely in the formula, does not depend on the previous hidden state, but it only depends on the input. Thereby, we, for example, have resetted it. We can do that, of course, not for, maybe we won't do that for all hidden states, but we want to do that only for some of the hidden states. So we might not say set the full matrix to 0, but some values. So think about what we had on the visualization with the LSTM. There we have seen similar things. Maybe you remember this one neuron, which was like active when we're inside a quotation mark and deactive otherwise. There exactly, you need this, that you somehow can reset. Oh, now is another quotation mark, so we have to reset our value to be outside. The other thing is we can also filter. That means we can ignore the inputs. If we want to ignore the inputs, we just set BK to 0. If we're setting BK to 0, we see that our new hidden state only depends on the previous hidden state and not on the output, and thereby it's working directly. So this first is quite nice and convenient. However, there is like one challenge in this. And we said one advantage of when going to state space models and no longer, and especially LTIs and not looking at RNNs, was that we can do this parallel processing. So we are not having to calculate one hidden state after the other, but we learned the parallel scan. We saw this example of the parallel scan, and thereby it's possible that we process all of them in parallel, or like not at least parallelize it partly, so that the calculation is significantly faster. And this is essential with new neural architectures. We saw that like it's important that you somehow take into account your hardware, because you can have a very great model, but if it's not somehow fast to do the calculation, you won't be able to process large data. So you might have good results on some toy tasks, but on real world examples where you benefit from using really large amounts of data, this is no longer possible. So the question is, can we somehow still use this type of algorithm still here? Because of course you can directly calculate this now easily with a normal forward process, but then you have the challenge that you can parallelize it again, and you have the same problems as we had seen with the RNN. So the question is, how can we still do it in parallel? And the nice thing is we can still use our parallel scan algorithm with one main change is we have to change a bit what we calculate. So before we saw we had the age, which we calculated based on the formula, and we could do that quite simple. This time it gets a bit more complicated. So we are defining some x prime, which is defined as ak, is a tuple, where the first part of the tuple is ak, and the second part of the tuple is bk times xk. That is the first definition. And then in the parallel scan, we have this aggregation function. So we have to check how we define the addition. And if we're adding up the two numbers, it's also a special one. So it's not the default one, but the adding up would be that the first term is then A2 times A1. And the second one is A2 times B1 plus B2. You already see a bit like recap of what is up there. And we will see that we are trying to have somehow in the second state, always somehow the hidden state in there. This might not look super obvious why this would work, and therefore it might make sense to have a look at one example. So we can do this now for an input sequence of length 4. So in this time, we have the input x1, x2, x3, x4, and we then have our matrices A1, B1, A2, B2, A3, B3, and A4, B4. What about C? Why are we not using C in here? So C1 to C4, we have like the final output is calculated as C4. Any ideas why we're ignoring that in the parallel scan algorithm? Not super difficult. Maybe the question is too easy that you're not. Why are we doing the parallel scan only on A and B, and we're ignoring C somehow? Yes? No, C can be any matrix again. Where I mean, in some cases it is one, that is true. But even if C is not one, you wouldn't use it for your parallel scan. Why? Yeah? Yes, so we don't need to think about the complicated parallel scan algorithm, as you said, but the second step of calculating Y from age, we can do it in parallel. It's the same multiplication you do at each time step, so you can just do it in parallel. So you don't have to think about any complex algorithm that you have to use there. You can just do everything in parallel. For the first step, for calculating the age, that is not possible. I mean, it's possible, but not that easy, because it depends on your previous hidden state. So there we need to do a bit more complicated algorithm. But for the second step of calculating our Y, we can directly do that. We don't have to think of any special algorithm. You just apply your CK on each position, and that's it. Okay. So with this, so we start here with A1, B1, X1. That's exactly the definition of what we said as our X primes. And then you see here already at the first position, now you have your H1 here, which is just B1 times X1, assuming now that H0 is just zero again. And now we apply our addition there, which says the first term is A2 times A1, and the second is A2 times B1 plus B2. And we're doing that in the parallel scan way. So we're doing it for the first and second one jointly, and for the third and fourth one jointly. If we're doing that here, we get matrix A1, A2 times A1, and then the second term is A2 times what was here in the second part, which is B2 times X1, plus what is here in the second one is B2 times X2. So this is just applying the rule up there on these two examples that we're having here. And if you look at this example now, this is what the hidden state at position 2 is. It's like A2 times the hidden state at position 1, that was this one, plus B2 times X2. So this is exactly the hidden state at position 2. And we can iterate that and do the next step. And you again apply exactly the same rule. So you take A4 times A3, what was here as hidden 2. This is put up there. And then you see the last two things are just what is here as a second term. And what we have then up here is exactly H4. And then we have calculated H1, H2, and H4. Anybody remember? Now we also need at some point H3. So how would we calculate that? Any idea? In the parallel scan, we have the two steps. So here I've only shown the up step. But if you remember, if we're going back, we have the up sweep that we have calculated now. And then we can exactly the same way calculate our down sweep. And there we would get all the other values. And then, so you again apply the same algorithm, the up sweep as here, and the down sweep. We have now detailedly done the up sweep, but then you also have to do the down sweep later with the same algorithm. And then you have, done this parallel scan on the LTI. So we are now able to very fast also calculate these types of hidden states, although they are depending on the input and the weight matrices are different from each other each position, so that we are able to ignore some inputs and so on. So are we done with the LTV model, or do you see any open challenges? If you would have now the task to implement it, would you see still anything which is a bit unclear maybe, or is everything? Could you sit down and PyTorch and implement this? So I guess one thing which is at least wouldn't be completely clear to me is still how do we calculate this AK, BK, and CK? So how, I mean, now before it was, I mean, it was easy if we have one A, B, and C. This is something you can learn. But again, this is a problem. If we have no AK, BK, and CK, it's nothing that we can just learn, because you want to be able to also use an AK 1000, although you have never seen it in training. If you would just learn each AK and BK individually, you could only have the ones that you have learned. And again, it wouldn't be very efficient, because if you would learn them all differently, most sequence positions might not have been occurred. So you want to have like some connections between them. and we need somehow an efficient way to learn the A, AK, BK, and CK. And at the beginning, we already said they should depend should depend on our input. And that is one big difference if we think about the LSTMs. There, this type of thing also depended on the hidden state. That we can't do, because then the parallel scan wouldn't work. If we would, because we have to be able here, you see, to calculate our A's and B's beforehand. We wouldn't be able to do that beforehand. We couldn't run the parallel scan. So you cannot depend them on your hidden state, but they only depend on your input. So how can you do that? We'll look into we'll just by example have a look at 3 different ways how this is possible. One model was proposed this year by Griffin, and it's like very similar to how it's done in the LSTM. The main difference is we have again some gates, but the important difference is in these gates, they only depend always on the input. They're not depending on the hidden state. To remember, in the LSTM, you had also read gates and forgot gates and input gates, but they always depended on HT and on the input. We can't do the HT here, but we only depend them on the input. That means then the final hidden state here is calculated as this HT, but we go there step by step and we have it nicely there in the picture. So the first thing in what we have is our recurrent gate, RT. The recurrent gate is calculated. Interesting. Okay, let's see how long it takes to see. You missed already one. I will repeat that. So we have the recurrent gate, which takes as a weight matrix on the input and plus some bias, and we have again our just sigmoid function. And this gives us R of t. We're not using directly R of t, but we are just calculating then an AT in this model by taking some diagonal matrix A times to the power of C times R of t in this one. It's just some hyperparameters they choose, but this is mainly then deciding on like where do we want to read from thing. And you see that, so AT here then is just multiplied, a multiplication of AT times the previous hidden state. You see that on the left column here. So you take X, based on X, you calculate this gate, and then you're multiplying not the gate itself, but the transformation of that with our hidden state. That is the first part. That is like, okay, how much from the previous hidden state you want to have. It's a bit like AT as then our A matrix we had before. The second part is a bit different. It's you take the input gate, the input gate is okay. Let's see what breaks next today. So the input gate is just calculated exactly the same way. The only difference is that we are this time have, of course, a different weight matrix, because you might sometimes want to read and take input or use it differently. Then you multiply your input with this, and then you're also multiplying it with 1 minus your input gate, so that you have there the difference. You see that again. So you're first multiplying it, the input with your input gate, and then multiplying it with 1 minus A of t, and then adding that to your hidden state. In this case, as you said, we don't have a C there, so our output is just again directly our hidden state. So yeah, this is one way of how you can do it. To use it, you see that it's very similar, or like somehow similar to an LSTM. A very important difference is that our gating mechanism is only depending on the input and not depending on our hidden state. This has Of course, you might now ask, why should it be better to have less possibilities? But the big advantage is, due to this less possibilities, we can do the parallel scan and we can efficiently calculate that. Another way of doing that is using what is called the RedNet with a linear attention. And here you see from the variables already, they try to do it a bit like attention. But the important thing is, differently to the normal attention, where you really attend to all the previous tokens and do a similarity. Since we don't want to do that, we want to have linear size, if you remember. So somehow keeping a fixed size summary all the time, and it's not dynamically created at each position. How it's done, you see again here. So it's similar. Based on your input, you calculate value, key, and query it somehow. But then, while you're not multiplying all the queries with all the keys, what you're just doing is you're multiplying your query, your key, and your values together, and add that to your hidden state, and your hidden state is somehow downscaled a bit, so that you have your new input, but you don't to not just always grow. You're like discounting a bit from your previous hidden state with gamma, and that is your new hidden state here. And then you're using your query to multiply with your hidden state in order to say, okay, these are the information they want to extract from the hidden state. You're seeing this time you're not querying like the full summary, but you have your compact summary, and you're only accessing that one to get the information. Again, you see that the formulas are somewhat related to what we had before. So in this case, the A is not depending on the time step. It's just a fixed one, but we have KT times VT. So you see here that there is like in the DK really depends on the current hidden state. And then you have a QT, which also depends on the current hidden state to be calculated. Any questions to this type of model? Okay. Then there is one model which got quite a lot of attention recently, which is called the Mamba model. And this does, again, as partly previously also has been done, it is motivated by looking at this problem of calculating our hidden state in a continuous space. So in the continuous space, you wouldn't have like a fixed HT times, but you would have a function which is continuous. And in this case, you would have then described your hidden state using a differential equation. So the derivation of HT is A times HT plus B of T times X of T, and the CT is the same. So this is the continuous version of what we had before as the discrete version. This type of continuous types of state space models is, I think, common in physics. And so it's a bit motivating this. And we'll see one specific implementation of that, which is motivated by the continuous one. But of course, then we have to again go to the discrete version, but because we have discrete values and have to deal with discrete. The motivation here is that in order to work well, you want to have like some HT, which is very good at approximating the near past of your model, and maybe still good as a very long past, but if things are very far away, it might no longer be that important, and you don't have to have like a perfect approximation of that. So you want to have some learning like this one, where you have your target is the black one. That is really the output signal you have. And you want to approximate it at each step with the red one. And you're seeing it's very good approximated at the very near. And then if you go far away, the approximation gets a bit worse over the time. You can do that. If you go further, then you have, again, a very good approximation very near, and the approximation in the far end is worse. And here again, very good approximation there, and it's getting worse. So it's storing all the important information of your input from the current, from the very near past, but it's storing less good the things which are quite far away in the way. And if we want to do this time, we have to think about this correlation between our discrete representation and the continuous representation. And how this works is to make a correlation between them, that we like sample our continuous function we have here at discrete time steps. And so you see that, so you have your continuous functions there, and we are sampling the values ht at different time steps. The important thing, or like what the model tries now to learn, is we are trying to a bit learn the sampling, like where should we sample. So it's not an equal distance, but the idea of the model is based on your x, you predict how big the difference is here, that you sometimes sample very near and sometimes you sample very far apart from each other. Yeah, if you're doing that, you have on the one hand, you have your t input here, you have your continuous signal, and on the discrete space, what we're doing is the same thing in the discrete approximation. And what we can do there is then again apply our parallel scan to efficiently calculate that. So what we have to do now is we have to like first have a bit one parameter more. See, we have a little less. So one parameter which is important here is your delta t, which measures the distance that you have between your points. So if you think of words, you're assuming your words don't have equal distance if you put them in a continuous space, but some are further apart and some are more near to each other. And then the idea is, so we have only one matrix A, which is fixed all the time, but we get our AK out of that in taking x of delta k, which is the distance between them, times A, and our B depends on the state and is calculated this way. So this is the idea of this type of Mamba models. What does it mean? So we have the two challenges, remember, where we had on the one hand the question, we want to do like filtering. So we want to filter out the input and ignore the input junk text. If we're doing this type of implementation, the idea is that in this case, we are trying to set our delta k to very near to 0, because if we are setting it to 0, our ak is xa to the 0 times a. So we have mainly 1. So a is 1, but b in this case is then 0. So in this case, we would just ignore b. So by having the definition from before, how we define our AK and BK, we can now still do the filtering by learning in delta K, which is very near to 0. We can also reset our history. That was the other way, where we try to have an A, which is mainly 0. This works if we are having delta K to infinity. Oh, this one is wrong. Sorry. So you have then infinity times A. If you assume that A is negative, this will result in a 0. So you have x of minus infinity, which is then 0, and you have your b, which is then a value. So you can also reset your history, and that somehow very nice fits to the continuous thing. So if you think of it, if you set your distance between 2 points to very, very large, then of course the new sampling point is not really influenced by the previous one. So you reset by setting this very far away. On the other hand, if you have 2 points which are mainly at the same time, you're ignoring the new input because it's mainly the same input you had before. Any questions to this type of parameterization of the model? Good. There's one last thing, and this is similar to what we had before in the KV cache, and there may be interesting, is somehow we of course have to do an efficient calculation of our model. So what we have, have, when doing all this calculation, of course, we have once our x and y's, which we need to calculate. We have then our the AKs, BKs, and H, and these are calculated based on our deltas on A and on B and C. So then it, of course, makes sense to first have a look on how big these are. So if we think of our X and Y's, they are like depending on the length of your time series and of course on the dimension of your input and output. For simplicity, now assume that the dimension is the same. So we have two matrices which are L times D there to store. Then our parameters we have here. So we have one fixed matrix A, which is depending on dn times n. We have the matrix bk and ck, which are lengths times n. So they're just vectors, they're not matrices. And we have our deltas, which are lengths times dimension. This is the efficient. What is the challenge is if we are now calculating our AKs, BKs, and H, this is, of course, might be not super efficient because these are quite large. And we said that if we are calculating these large matrices, this might be a challenge because we might not be able to store them. So a naive approach would be, so you take your deltas, B's, and A's, calculate A's, A dash and B dash from that. Based on that, you get then the input, calculate your H, and then you calculate based with the C your Y. Based on what we learned before, do you have any suggestions how you would do this more efficiently? Let's think about last week. I think we had it last week. Any idea? So it's again might make sense to not really initialize all the H and A dash and B dash in total, but fuse the operations to calculate them only for part of your sequence directly and not store them completely to be more efficient. So here you see that again, how it's done. So it's based on your, this is, you have again the X, the BT, X, delta T, and so on. And you see that the HT is here kept in the, only in the internal memory, and the other ones which are stored for longer, they might be stored where else, but you're not keeping all the HTs over the time, but only keeping them for some time. Good. So what you should remember from this lecture is on the one hand, what are state space models, how they can be used. Then we had, it's a bit long, it's last week, I know, but we had this recurrent and convolutional view, and that is very helpful. We'll see later in training where you have everything available. It's good to do the convolutional view, to do the processing in parallel, while in the recurrent view is good when you're getting one input at a time and you don't want to store all the history. Then you only have, you can use the recurrent view and don't have to store the full memory. We've seen that you can again do hardware-aware architectures, and really a big motivation of doing these types of models was to do them based on to really address directly what are the needs of current GPU hardware. Do you have any questions before we are going for the last part for today? Good. One moment. Just have to switch. Okay. So yeah, as I said at the beginning, we now want to finish this section about architectures on looking at what type of sequence models we learned, what are their different properties, where they are similar, and especially also how they are used, and how they are maybe also combined into larger models. Just to recap, what these sequence models typically, what we all had here now as an example, is we're trying to normally do this type of one-to-one mapping. So we have as an input a sequence, and we're generating some type of sequence. And we saw that, if you remember, for example, in the vision transformer, that doesn't really need to be a sequence. We can also have another type of structure, then make it into a sequence, and then generate that. But this is somehow the thing we're typically talking about. What we're then doing is normally we have this one-to-one mapping. So we're generating one hidden representation for all our inputs. So there is a vector input, a sequence of vectors as input, and a sequence of vectors as output. Why we couldn't use standard feed-forward neural networks, we said, is that on the one hand, we have here variable size. So we have to deal with inputs which we haven't seen in training. And also we want to somehow use local structure. So if we learn something for the first position, that might be also helpful for some other position. So it shouldn't be that everything is like independent. This also means with the type of models we are using here, we are inputting there some type of structural bias. So if you're thinking about like an RNN, so you're processing as a sequence, you assume that there is some of this is important. And for example, there is an implicit bias in there that the previous one is more important than what is far away, because you're just easier to learn that. And you should be always aware of that. Or like if you CNN, you have this direct thing which is a shift invariant, and where it's unimportant where it is in the end. The examples we learned can be grouped mainly into three things. So we have the TNN and CNN, where the idea is to apply the same operation at each position. So here is like one example where we had a kernel size of 3, and you shift it over it and always apply the same operation, and then you get there a hidden state by doing that. This is one way of how we can do that, and how we can generate a new sequence based on our input sequence. Remember, in order to keep the sequence length exactly the same, we needed to like do some padding in there. So we can also apply this type of kernel at the first and last position. But in general, we're also doing this type of one-to-one. Then a second type of model or type of architecture are recurrent neural networks or state space models, where the idea is not we're applying again similar operation or the same operation at each position, but in addition we have this global context stored in a fixed size representation, which is our hidden state and which is shifted over the time. So we're always storing what is all about important about what we have read so far in an additional memory, which we can always access at each position. We had there two main things. We have the RNN, where we have nonlinear connections between the states, while in the state space models, for example, in the LTI, we have linear connections between them, and then we're able to process things faster. But like more from a model view, when we are now ignoring calculation things, it's somehow similar. We always have this type of memory which stores everything which we have reached. And then there is the third thing which we have, and that is the self-attention, where the idea is that at each position, we are looking at all the other positions, we're making a new summary of all the other positions and using that to as a new hidden state. So in each time step, we're not like having some memory stored, but we're somehow generating independently at each time step a memory of the full sequence and using that. And this is the self-attention mechanism where we do this type of summary at each step. So these are the three big groups we looked at. And of course, they all have advantages and disadvantages, as we have learned already, how computation efficient they are, and how much processing they need, how the information flow is, how fast they can learn. And I mean, it depends on, of course, also on the task, where they are successful or not. I mean, currently, self-attention is very successful, even in different modalities, so in vision and in text. But for example, RNNs were a bit more successful in text, while CNNs were often used in vision, and vice versa, they're at least not so commonly used. And therefore, it's also important to look on like what is the difference between them. And one important difference, of course, is the type of receptive field they have. So what influence our current hidden state? If we're looking at the TNN and CNNs, then we are only influenced by a local context. So by everything which is around that, but it's a fixed size local context, can be very large, depends on how you define it, but it's always clear that you have some type of fixed. In the RNN or SSMM, you have like all the previous sequence. So typically it depends on everything which was there before is influencing your current hidden state. And on the self-attention, we are influenced by the whole input. So at each time step, we can look at everything else, and each of the tokens are influenced by all the other tokens. On the other hand, one other important difference is the direction. So there is some concept of direction in the RNN. We are processing from left to right. So there is a left to right direction. While in the TNN and CNN or in the self-attention, there's no really a notion of direction. There's a bit on that on the CNN because it's like shifted by one always, but in general, there's not really a direction on that. Does that lead to some problems, for example, by the self-attention, that there's no type of direction in there? Remember, you had to do some hack to put this notion in there again. Yes, exactly. So because there is no notion of this, where the things are, this is, we had to like explicitly put them in there with the type of position encoded. In an RNN, you don't need to do that because you have the notion in there from left to right, and therefore it's clear like at which position you're currently. So now these are the basic things. So the question is, how can we really, or what are the typical use cases there? And we want to look at two, one's on encoding things and one's on generating stuff. So one typical example where this is used is to encode some type of input. And where you have input which might have been variable size, the input can be text, the input can be audio, that can be often even images. And the idea is we want to generate at the end some type of hidden representation where you have one vector for each input, for example. We call these types of models typically the encoders. So we're trying to encode all our information in order to generate some type of hidden representation. And yeah, this is where if you have today a work, for example, you can put the words in there as one hot encoding, maybe embeddings, and then you have an sorry, you have an RNN here as an example, but you can also have a CNN, you can have a self-attention, which takes its inputs and generates a new sequence of hidden states here, which represents somehow your input. So you're encoding your words as some type of hidden representation here as a sequence of vectors. And of course, this is typically not the final test, but it can be very helpful to do either classification, sequence labeling, where you want to generate some type of token for each of them. So in all these cases, you need to have an encoder which generates a sequence of states which somehow encodes the most important information. And the important information part is now the hidden state here no longer depends only on the word, but also on the previous one. So the nice thing is that we encode the context. And for many real world applications, it's important that you're not only knowing what is currently happening, but what also is happening around to understand the meaning of each input based on the context. And that's exactly what you can do in an encoder, so that you have all your information encoded in there depending on the different position. The second type of model is where these types are often used is what is referred to as an autoregressive decoder. And here the task is not to encode an information, but to generate a new structure, in this case, typically a sequence, so that we're generating a sentence or any type of other, an audio sample or so some type of sequence. And it's called autoregressive because often it's helpful to not generate the sequence directly at once. So like predict, oh, I want to predict 10 words and then generate the 10 words in token, but to do that step by step. Because based on your previous decision, maybe your next decision is different. So if you have some type of process which generates things or generate actions one by one, it's often helpful to have this step-by-step approach. Because typically you're also not directly predicting the action, but your network predicts a probability distribution over the action. Then you select some of them. And then, of course, it's important that it knows which one you select. So how does it work? So we have, again, we want to generate. So we have to put something into the network. And the typical thing you do is you put in there sentence start. So start generation. So we put into the network start generation. You see here, you have, again, nicely an RNN, and then you generate your first token. So you get your input, combine it in the RNN, get your hidden state. Based on your hidden state, you generate your no token. How that typically works is you can't generate a fixed token. So you generate a probability distribution over all your tokens. Like you have a one-hot encoding again, but now it's a probability distribution. And then maybe you select the most probable one or anything like that. Because typically your network can't do like a discrete output, but it generates a probability distribution over all outputs. So in this case, it's a probability distribution over all your tokens. So now you have generated today. And then, of course, you have to tell the model, oh, it generated today, because it didn't generate today. It only generated a probability distribution where maybe today is the most probable one. Then you're putting today in, again, calculating your new hidden state. Now it knows, okay, now we have a sentence starting with today. And so it knows, okay, how can I continue it? It maybe says I. And this way you generate step by step, always putting in the previous token. And then you stop when the system says, oh, this is the end, with a somehow end of sentence. So this is the type of decoder where also these types of RNN models are often used to generate a token. There is one big difference you already saw, is that in this case, not all information are there at the beginning. So what we typically have is that we only have like get the information step by step, because our new decision is depending on the previous decision. So that's what people refer to as autoregressive. And it means, we have to do this calculation step by step. So we can't parallelize things. That is what we saw before, where you might want to have a state space model, for example, and where maybe the big advantage of transformer that we can do parallelize everything doesn't exist anymore, because we cannot parallelize things. So in training, you cannot do because there you have everything available. But during generation, during inference, you don't have everything available and can't. Any questions first to encoder and decoder? Now, there's one thing with this. A decoder by itself is not that super useful, because it just generates some random sentence. Normally, you don't want to generate something, but you want to tell the model generate something based on this information. So that can be, for example, generating machine translation, generate a target sequence, but not any sentence in the target language, but which has the same meaning as a source sequence. In a dialogue model, it's not generating an answer, but generate an answer which somehow matches to your question you got. Or if you have text to image, generate an image that somehow is matching the described text. Or in automatic speech recognition, it shouldn't generate just text, but it should generate text, which is a transcript of what was there in the audio before. So therefore, we don't need general generation, but we need conditional generation. So we want to generate something based on some other information we had before. And for this type of conditional generation, there's like, you can know what we have learned before and combine them either into what is referred to as encoder-decoder models or into decoder-only models. So let's start with the encoder-decoder model, because it's somehow quite nicely there. If you have a question, where is Karlsruhe, then you want to generate the answer in Germany, but the answer is like somehow generated based on the input you have. But we learned just the two components for that we need. So we have our input. We need to somehow encode that. There's an encoder for doing that. And then we want to have a decoder, which is generating our output here and generating it. So we have the two models, one an encoder, which takes the input, and then a generator which generates the output. There's only like one challenge with this. What do we need now to do? Yeah. Yeah, we need to, I mean, of course, train together. So you can, that's a good point. So in training together, it can be that they are partly trained individually or they are all trained together. That is kind of, but first, from the architecture point of view, the big question is we need to somehow connect both of them. So we need to connect both models. And therefore, there's, again, different ways of how we combine them. Does anybody have any idea already? Yeah. Yes. So in more, if we're coming in Centaur, that is more I think the vision view on that, and on vision task, on text representation task is often the fixed representation, but it's the same idea. So what we want to do is we want to somehow generate some representation based on the input and copy that to your decoder then. If we have an RNN, this is the typical thing what you do. So you take your RNN, and then you take your last hidden state, which should be like the summary of the full sentence. So we had said the RNN is like collecting all the information. So at the end, the RNN has all the information about the full sequence. What we then do is we're taking this one and using it as our initialization for the RNN in the decoder. We can just copy it. We can also do a linear transformation. But now you have here the hidden state. The first hidden state is no longer like fixed, but it's like everything we have from our RNN before. And that means, oh, in this case, we're now generating based on the first hidden state. And the first hidden state is what is there from the encoder. So this generation is now based on the encoder. So we're decoding something, and it depends on the encoder. So that's exactly the test. So we're getting some input, and we're generating based on the target side. So this can be done with an RNN. You can also generate this fixed size, of course, with some type of TDNN or CNN, and like doing some pooling at the end. You just need to have some type of fixed representation here, and then you can use this fixed representation up in an RNN. So that's very well suited for doing this type of generation for based on an RNN. Any questions to that? Yes. Yes. So this is just a vector. And I mean, we always had our h of t, h0, which we wasn't always question what we do. I mean, typically you can take all of 0. So, and now we just take the first hidden state here is just the last from there, or some weight matrix times that if you want to have extra calculation in there. The other way of doing it is going to our type of attention we had. We always called it self-attention. So there needs to be some other type of attention. And the idea is before we always had the query key and value from all the same. But you can also do it differently. And then you're like always putting information from the encoder to the decoder. So the idea is your current hidden state in the decoder is your query. So you're taking this one saying, oh, this is my question. I want to know more how to continue. And then your key and values are your hidden states of the encoder. And then you're comparing your query to all your keys here, asking from the encoder which information are currently important to generate the next token. So you're comparing your query to the keys here, looking which one is the most important one. If you have done that, then you can multiply your similarity with your values. You get one final vector and you take your final vector to the decoder. So that means then that you can use them there in a feed-forward network or anything. So what you're mainly doing is at each time step in your decoder, you're looking back at your encoder, you're seeing what is important currently there, which information should I get, and then taking them back. So that's the main difference. That's why we highlighted fixed representation beforehand. Before we had one time chance to transport information from the encoder to the decoder. There's a one chance and where all the information has to transport. In this step, each time you generate a token, you have the ability to look back, take, oh, this is important at my current position, and use that then for generating the next token. And so, yeah. No, that's why we don't, it's not self-attention, it's cross-attention. So that's a very important difference. So in self-attention, you have query, key, and value, which are all generated based on the same token. In this one, your query is based on your decoder hidden state. The decoder is asking what is important. Your query and values are from the encoder. They tell you what should I get, and then you're using that. No, they are trained end to end. So this is not trained, that's completely different layers as before. It's a new layer which only does a cross attention. So it's a cross attention layer which allows us to get information from the encoder into the decoder. We are seeing one example. So this is typically combined in the transformer, and we'll see there one example very soon. Then there is another idea, one last thing on conditional generation. These are models based purely on decoders. So they're called decoder-based models, not surprising. And the idea is, yeah, we just only have a decoder. The question now you might have, how should it work if we only have a decoder? The idea is you start your sequence with your input and then just let the model continue with its own answer. So this is what people nowadays call the prompt in large language models. So this is a decoder-only model is what a language model is. So you're generating word by word, but at the beginning for the input, you not let it generate what it wants, but you force it to, you give it always the input that you have already, because it shouldn't invent new input. So for the input part, the decoder is just fed with what it should get. And then then once you say, okay, now start generating, then you're inputting what it outputted. You see on the left part, you're ignoring the hidden state. You're not putting there, you're ignoring what it would output. In this case, you really have like just one single model, and you're not having like these two separate encoder decoders. You have one model which should do both, encode what is at the input and generate then what is the output. So you can view it as a like, please continue the story task. So you have the input, and the model should continue it in a way that then the answer is there. So a bit like, maybe, you know, I don't know the English term, Lückentext in German schools, where you have breaks and you have to fill out them there. Any more questions to these types of models? Good. So now we have the overall types of models, and then, of course, then motivate some additional challenges to the model. One thing we already had is like the nice thing about neural networks, you can make them stronger by making them bigger, by adding more parameters, because then they are more powerful. In neural networks, there's two possibilities of that. You can make your hidden states bigger, so make the network wider. So instead of having here a hidden state of 100 dimension, you make it 200, 500, or anything like that. This gives more parameters, more to learn. Of course, that you need more data to learn that, but this is one way. The other way, which is also important, is having multiple layers, so stacking layers on top. We have seen that in the very basic lecture already for basic neural networks, but of course, this is also possible for any type of other neural network. So here's an example for the RNN, and the same way you can do it for self-attention and all of that. And the main idea is that you want to, improve the capacity of the model so that it can, work in some way better. How that works, so the one layer RNN we said is like your hidden state at position T is a function dependent on the previous hidden state, on the current input xt, and on our parameters. We had, for example, in the SMM, we had this function like ht is like a times ht minus 1 plus b times xt. So then a and b would be our theta. In the multi-layer, it's quite easy now. So we have several, for each layer, we have mainly the RNN function, which now depends also on the current layer, which means, of course, you also typically have parameters different from the different layers. So your A is different in the first, second, or third layer because you want to do something different. And otherwise, it's mainly the same, only that now our input is no longer our original input, but it is the hidden state at the same time, but at the previous, in the previous layer. You see that nicely here. So we have here this hidden state gets as input the same layer, but the previous time state, and the previous layer, but the same state. And these are then combined to our new hidden state. And then importantly, of course, the original input is then the hidden state below the first layer. Yes? Yes, yes. So you have to, do the right choice. So it's the same thing in all types of neural networks. The more parameters they have, the more problematic overfitting gets. You can address that by having more data. That's the easy solution. Then there's different types of training strategies. We will come to that, like dropout and other things. So you have to definitely address that and prevent overfitting. However, otherwise you might have underfitting, especially if you have large data, your model doesn't have the capability, then it can't learn it. So that's definitely important. This is first just, okay, this is one way to improve the number of parameters, but there is, not an easy thing of what is the right type of model size we can have. If we think of convolutional neural networks, there's one additional reason why you might want to stack layers. And this is if you want to reduce the sequence length. So in CNNs, if you have a stride which is bigger than 1, then you can also reduce your sequence length. So here's an example with a stride of 2. So you see that you're not calculating always all hidden states here, but you're always moving by 2 positions. And that means that at this next level, your number of hidden states is reduced by 2, and then in the last one, reduced by a factor of 4. So if you have very long sequences, we often see that at the bottom, you often have some type of CNN layer that somehow reduces the sequence length and like does more a compact representation here so that you have it. And there it's often like of advantage if you're not directly try to put everything into one hidden state, but you do like it in 2 or 3 steps by always reducing them by a smaller factor. Of course, you could also do that in one step by having a stride of 4 and always going just 4 apart, but it might be advantageous if you're not doing everything at once, but you're doing it like step by step. Any more questions about? And then there is the last thing here is the transformer architecture. But we won't look at all details yet. But one important thing is, of course, you can also stack different types of layers. And that is what is typically today done. For example, often you put in standard feed-forward layers in between to just have additional processing capability. So you then apply the same type of feed-forward layer at each position. You can also view it as a CNN with a kernel size of 1. So you only look at the current hidden representation, and you have additional capacity by like doing calculation on that. So this is here how a transformer looks like. So what you have here, you have positional input, then you have positional encoding. Then these 3 should visualize that you have a self-attention layer. So you applying the self-attention layer to all your positions. You get your hidden states, and then these hidden states are not directly there, but then you apply on top a normal linear transformation, so one layer of a normal MLP, and have an additional calculation for that. And then this whole block in blue is not done once, but people refer to it as a transformer blocks. So then you stack this type of blocks for n times. So you get the input and put it again as output. And you get the output and use it again as input to a new type of layer with different types of parameters. And you're stacking this type on top of each other again and again and again and again. And in the decoder, you see it's even more complex. So what you're having is first you have a self-attention layer here. Then you have this type of cross-attention, which we said before, which takes your inputs and looks at the encoder to see what is important now. Then you have a linear transformation. And then again, these whole 3 blocks, you take as a block to stack onto each other's time after time, and that's your final transformer thing. So you see that here you're stacking several layers and even different types of layers. Of course, you can also combine RNNs and self-attention or all the different things in different ways. You always have to view what is my input and does it fit to my output. Yes? So this is like should visualize the hidden states. And so that if there are 3 together, it's an attention. The first one is a self-attention, and the second row is a cross-attention. You see that now the key and values are coming from there, and then you have a linear layer on top of that. Yes, each of them a layer, and then the transformer layer is normally referred to as the combination of these 3 layers, and you stack them up several times on top of each other. The green one is a transformer layer. It's based, this should visualize a self-attention layer. This should visualize a cross-attention layer. And this should be a linear transformation. So yeah, in realistic models, it's very important to combine different types of models. For example, in the Mamba model we talked before, they also combine the state space models and have one self-attention layer in the middle. So they combine like state space models and self-attention. So that is a nice thing here. You can combine them. Of course, you should keep two things in mind. On the one end, you want to do efficient computation. So does it work good that you have good computation? If you have the CNN to do everything in parallel, but then you have an RNN in the middle, it means you can't do the parallel processing anymore. And of course, it should add some good capabilities and should be helpful. Good. Any more questions? Then one last thing, and that is like how we're doing the information processing. And there is again the difference between the encoder and the decoder. So if we're thinking about the encoder, we said the nice thing is that all information are available. That has the one advantage that we can do things in parallel. So we can parallel process everything in directly. But it has also another effect. It doesn't mean not only mean that we have all information in parallel, but it also means that information can flow in both directions. So what we have as representation of our first word does not only need to depend on the previous word, it might also depend on the future words. That's a very big difference. If not all information are available at the beginning, you cannot make your representation of the first word dependent on the third word because you don't know it yet. In the encoder, all information are there from the beginning. So your full representations can be based on all the previous representation. However, if we are thinking of an RNN, we are not really using this ability. So if you have an RNN, we said that our hidden representation depends on the previous hidden representation and on our input. So we have a unidirectional model. Your third hidden state here only depends on position 1, 2, and 3, but it doesn't depend on position 4. That is cool. So unidirectional means your hidden representation always depends only on the previous models, but it never depends on the future model. And that is, of course, somehow a limitation which we don't need in the encoder. In the encoder, all informations are there from the beginning. So why not look at the future in order to understand what this means? It might be that it's easier to understand what here is standing if we look at these parts also. So the question is, can we also integrate this type of information? If we now want to stick first with an RNN architecture, do you have any suggestions how we could do that? Yes? Yes, so it's not, that's the main idea. It's not directly possible. So the easiest, the one thing you can do is not add an arrow backward, but you can have a backward RNN. And the only difference is now from the formula is your hidden state depends not on the previous hidden state, but on the next hidden state. So in the sequence. So you mainly have changed the order, and now you're calculating from back to the front. So your fourth hidden state depends only on the initialization. Your third hidden state depends on the fourth hidden state. Your second hidden state depends on the third hidden state, and the first one on the second. So this is the first step to that, but we haven't really, it's still a unidirectional model because this model now, yeah, it doesn't depend on it does include the past, but now it ignores all the future. So the state at position 3 depends on 4, but it no longer depends on 2 and 1. So it's a first step, but might not be the direct solution yet. Yes? And that's exactly what we're doing. It's called a bidirectional RNN. That's a perfect answer. So you stack the two together. So your hidden state at position T is your hidden state of the forward model concatenated with the hidden state of the backward model. And then you have these two hidden states together. And now if you look at them, you nicely see it in the picture. Now your hidden state at position 2 depends on position 1 over the forward model, so the upper bound, upper part of the model, and for the lower part, it depends on the thing. So at each position, you have a summary of the full sequence. So you have information to all the context and can use all the context. Of course, this is only possible in encoder style information, where all informations are there from the beginning. If you don't have, if you generate word by word, you can't do that because you don't have all information available there. Maybe one comment you said we can just add an arrow there. That is not as simple. Like I mean, maybe the easiest thing would be to have in our forward model just arrows in both directions. But if you look at the formula, that would mean that HT depends on the previous hidden state and on the future hidden state. And then you have there a recursion, which you cannot no longer directly calculate, because then hidden state 1 depends on hidden state 2, and hidden state 2 depends on hidden state 1. So how do you calculate that? I mean, of course, there's like special algorithms to like do some type of annealing to do that, but it's at least no longer directly possible. So you can't directly then calculate your hidden state. And that's why it's important to have a direction, but you can circumvent that by concatenating them. And now you have information at all positions and can use them. Of course, it's one challenge is here that for the one direction, you need to calculate them from the forward, and from the other direction, you need to calculate from the backward. So in this case, it might be challenging for doing this type of thing efficiently. Okay, so what about the decoder side? What type of processing can we do there? I guess I said it already before now. So if we generate target by token, we can only use unidirectional model. So in this case, we cannot generate like do a backward RNN, for example, because we don't know what the future is when we generate the current token. If you think of this decoder model, here again, it would be really bad if we want to generate in here and we would have a backward model. It would depend on that later we generated in. So we can't generate something based on that we already have generated it. So on the decoder side, we really have this causal relation so that it has to be depending on privacy. So we can't do bidirectional processing here, but we have to do unidirectional processing. What does it now mean? If we want to use self-attend, I mean, for RNN, that is no problem. We just can't use a bidirectional model, but we have to use a unidirectional model because we can only like process it like one by one. That's easy. But this time, the challenge is the self. Good. Now you've seen the solution already. Okay. So the bidirectional model, you see, you always compare all keys to all queries. So information, we said, that's the nice thing about the self-attention, that information are flowing in all directions. So for calculating your second hidden state, you're querying based on your second input, but you're querying all the other states. But in a decoder style, this is not possible because you don't have the other states. You don't, at second position, you only have 1 and 2, but you don't have the past. So you have to do that a bit differently. And that is what is then referred to as the mask attention. So that means you're only attending to yourself and to all the previous ones, but you don't attend to the future. So if you look at that from the matrix view already, it's very nicely shown that you only have the diagonal. So if the query, if you're at position 1, you want to calculate the first hidden state, then the first state is your query. And then the only information you have is also your current state. Your key is only 1. If you have at position 2, you can query, as in this image, you can query position 1 and 2. So you can get information from 1 and from 2 and use both of them to calculate the new hidden state. If you're at position 3, you can use 1, 2, and 3. And at 4, you can use then everything. But you can only always look back to the past. And the only restriction we have to do there is to change our attention metrics. So which querying keys are combined, and then we can restrict ourselves from a bidirectional model to a unidirectional model. You know, think about the parameters, and you see, now we've seen we can do the self-attention bidirectional and unidirectional. We can also do the RNN bidirectional and unidirectional. If you think about the parameters, do you see any difference? How many parameters you have in the RNN for both directions and one direction, and you're doing the same thing for the self-attention. Yes, and for self-attention? Yes, exactly. So for self-attention, the number of parameters is exactly the same. The only difference is mainly, if you think about that, you can't even calculate how it's implemented. In training at least, you're even calculating exactly the same thing. If you do the normalization, you put these values to 0, then you've ignored that. So then the parameters here is exactly the same. And as you correctly said, for the RNN in contrast, we have an RNN to the front and we have an RNN to the back. So we need to double our parameters. Doing the combination doesn't need any parameters, it's just putting it together. But we have all our parameters of the forward RNN, and we have all our parameters for the backward RNN. So we have different parameters in doing that. For the self-attention, it is the same. So theoretically, you could even share parameters and use the same parameters for mask attention and self-attention. However, that normally wouldn't, of course, work that well, because if the model is used to normal attention, it will work good on normal attention, maybe bad on mask attention, and the other way around. Yes? This is now nicely going to the next slide. So this is the mass self-attention is not the cross-attention. So we have here 3 attention layers. And what I didn't say before is that these 2 self-attention layers are not exactly the same. So I said we have 5 layers in the transformer. We have on the encoder attention, 5 types. They may be repeated several times, but really 5 times. We have a self-attention layer here. We have then a feed-forward layer here. We have a self-attention layer here. Here we have the cross-attention, and here we have the feed-forward layer again. Now the difference is these 2 layers. In the encoder, we can do the normal self-attention where we attend to all the other tokens in the sequence. Because on the encoder, we have our input, and our input, we assume it's available from the beginning. In the decoder, we're generating token by token. Therefore, this can't be a normal self-attention, but it needs to be a masked self-attention, where we only attend to the previous tokens of the decoder. So here, we are taking our current word on the decoder and attending to all the previous words of the decoder. Then we have the cross-attention, where we take our current hidden state and we attend to all the source words. So here it's completely different. The query is from somewhere else from the attention. But of course, here we have a full attention. We don't need to mask anything. And then we have the feed-forward layer there. Yes? Yes. So you can do RNNs both in encoder and in decoder. You can do self-attention both in encoder and decoder. That is very important. So very good point. So you can have cross combination. You can RNN-based encoders, RNN-based decoders, self-attention-based encoders, self-attention-based decoders. The important thing is if you're in an encoder, your RNN can be uni or bidirectional, whatever you prefer. On a decoder, it cannot be bidirectional. It has to be unidirectional. For self-attention, the encoder can be normal self-attention. For the decoder, it has to be masked self-attention, where you're not looking into the future. Yeah, so thanks. I think that summarizes very well the different things. So always keep in mind what you can use. Do you have access to all the information? Do you need masking in there in order to use the right type of layer in the right part of model? And yes, with this, we are somehow finishing our part about the different architectures. So we looked at very different architectures today. We compared them. We looked what need to be specified. So in general, you can use RNN and encoder, decoder. You can use self-attention in both. You can also use attention to combine different types of models. However, if you change, you always need to do minor changes like going to mask self-attention or anything. Two important components are often encoders and decoders, where the one is about understanding what is in there, and the other thing is about generating something new. Do you have any more questions? Good. Then thanks for coming. And then on Thursday, there is an exercise. Then have a nice break, and then we'll see each other again for training.